Hi everyone, welcome back to Chem Help ASAP. In this video, we are going to do several types of calculations with weak acids and bases. So this will include things like calculating the pH of a weak acid or calculating the pH of a weak base. Also, we're going to deal with how do you calculate your Ka or your Kb, and also how do you handle a percent dissociation. Let's get started. So remember, when you have a weak acid or a weak base in solution, it's only going to partially dissociate, as opposed to, again, a strong acid or a strong base, which is going to completely dissociate. This is what makes these calculations more challenging than calculating, say, the pH of a strong acid. All right, so here is our problem. We're going to calculate the pH of a 0.55 molar solution of hydrofluoric acid, and we have the Ka for hydrofluoric acid. Hydrofluoric acid is a weak acid, therefore it is going to set up an equilibrium in aqueous solution. So the first thing I need to do is I need to get that equation for equilibrium. Here is my equation right here. Again, in equilibrium, meaning you have your forward and your reverse reactions going. And you can see I have already put this equation in an ice table because it's in equilibrium. So initially my concentration of hydrofluoric acid is the 0.55 molar, and I don't have any products yet, so those are 0. Which way is the equilibrium going to shift? Well, it's going to shift towards products. I have no products right now. So my consumed is going to be minus X on my reactant side. It's going to be plus X for both of my products. And then my equilibrium concentrations, again, I'm just adding down the column here. This is very much how ice tables go. We set up our ice table for our weak acid like we would set up ice table for anything in equilibrium. Once we have our ice table, we can write our K for this reaction. Now, this is a Ka because it's an acid, but you can treat it just like a KeQ. This is going to be products over reactants. You'll notice I don't include water in this. Because our concentration of water can be considered constant, it's actually folded into the constant Ka here. So we only need to worry about the concentration of hydronium, fluoride, and hydrofluoric acid. Well, I have those equilibrium concentrations from my ice table right here, and I also have my value for my Ka. So I'm going to plug all those numbers in. Here we go. So here's my Ka, again, plugging in all of my expressions for X right here. Now, at this point, I'm thinking, I've got a quadratic and I really don't want to have to deal with this denominator. Can I simplify? Our very general rule of thumb is if your Ka is 10 to the negative third or smaller, you can drop your minus X. But when we are finished with this problem, we will double check this assumption. So I am going to drop my minus X and simplify my equation. Here is my new simplified equation, still a quadratic, but much easier to calculate, right? So solving for X, I get a value of X of 2 times 10 to the negative second. Now, at this point, students often forget what X means, especially if you've had to solve a full quadratic and you couldn't simplify it. You're just so tired by the time you get to X, you're not thinking about what X is. So let's remember what X is by going back to our ice table. Remember, X is what we use to say how much was consumed, but it's also the concentration of our hydronium and the concentration of our fluoride ion. Now we're trying to get pH here, so having X be the concentration of hydronium is where we want to go. So our value for X, again, is 2 times 10 to the negative second, but that equals our concentration of hydronium, which connects into pH. Remember, pH is negative log of hydronium. So I just need to plug my value for X in for my concentration of hydronium, like so, and I get a pH of 1.7. Now, this makes sense. I have an acid in solution. I should have a pH that is less than 7. So always make sure you do that little reality check there. Does your pH make sense? We did make an assumption in this problem. We assumed that we could drop this minus X. We need to check that. And we're going to check it with the 5% rule. So our value for X over our initial concentration of our hydrofluoric acid times 100% should be less than 5%. If it is not, I need to go back and redo that calculation with that minus X in there. So plugging in my value for X, here's my initial concentration for hydrofluoric acid, and I get 3.6%, which yes, is less than 5%. So my assumption is good, meaning I don't have to go back and recalculate everything. This is my final pH. Let's see how these calculations work when we have a weak base. All right, so here is our new problem. We need to calculate the pH of a 0.3 molar solution of ammonia, and we have been given the Kb for ammonia right here. It is a Kb because, of course, ammonia is a base and it is a weak base. So I need the chemical equation for what is going on in aqueous solution with ammonia. So here is my equation right here. You can see I'm already setting it up in an ice table. I'm going to be forming ammonium and hydroxide. Again, still in equilibrium. Ammonia is a weak base. Let's plug in for my initial. So my initial concentration is 0.43 molar per the problem. I don't have any product right now. For consumed, this is going to be minus X plus X plus X. Again, it should be obvious which way the equilibrium is going to shift here. I have no product initially, so it's going to shift right. Then to get my equilibrium concentrations, again, I just add down that column. And now I've got my ice table all filled out. I'm ready to plug in for my expression for Kb. So let's first just write that expression. So Kb is equal to, again, products over reactants. So just like with Ka, this concentration of water does not show up. It's actually folded into that Kb. I do have my value for Kb. It was given in the problem. So plugging in my value for Kb plus all of my X's here, this is the expression I get. Again, just like before, I'd really want to get rid of this minus X. And because my Kb is 10 to the negative fifth, I am going to drop that minus X. But of course, when I am finished with this problem, I am going to go back and double check that assumption with the 5% rule. Okay, so now I have a much easier expression to solve. Solving for X, I get 2.7 times 10 to the negative third. Okay, again, connect that value for X with what is going on with your ice table. What is X? X is how much we consumed or what our change was, but it's the concentration of our hydroxide. This is what we're going to connect into our pH. So our X is 2.7 times 10 to the negative third, which is equal to our hydroxide concentration. How do we use hydroxide concentration? Well, we're going to calculate pOH right here. So I'm just going to plug my value for X in, and I get pOH is negative log of 2.7 times 10 to the negative third, which gives me a pOH of 2.56. I do want to point out, be really careful here, because very often students, when they get X, they just slap in a negative log and then they move on. You have actually calculated pOH here, not pH, and hopefully, again, there should be some red flags waving if you think this is a pH, because we should not have a pH that's acidic with a base. So again, those logic checks are really important. We have calculated a pOH, but the problem asks us to find the pH. So we're going to use this equation right here to convert our pOH to pH. Again, just plugging in our numbers, and we get a pH of 11.44. This makes a lot more sense. For a pH for a base, it should be greater than 7. Okay, but we're not quite finished yet, because remember, we made this assumption over here that we could drop this minus X. Let's double check that with the 5% rule. Okay, so we're checking our 5% rule. Again, our value for X over our initial concentration of ammonia times 100% should be less than 5% if our assumption is valid. So plugging in my value for X, here is my initial concentration times 100%. And yes, that is 0.63%. It's less than 5%. Our assumption is valid. We don't have to go back and redo any calculations. I just want to repeat again, when you have a base and you're calculating pH, your pH should be greater than 7. Always do those reality checks. Now let's look at a similar problem, but we're going to be given different information here. Our problem is, what is the Ka of cyanic acid if a 1 times 10 to the negative second molarity solution has a pH of 2.77? So we're still dealing with a weak acid, we're still dealing with equilibrium, but in this case we are going to calculate Ka and we are given pH. Just like before, I'm going to start with my balanced chemical equation. What is going on with cyanic acid in aqueous solution? So here is my balanced chemical equation. Yes, it's a weak acid, so it's producing hydronium and it's producing its conjugate base here. Okay, let's fill in our ICE. Initially, we have a 1 times 10 to the second molarity concentration, and we have no product. Our change is going to be minus x, x, and x, just like before. And again, our equilibrium looks just like it did before. Okay, this is all great. It's all coming together just like the other two problems did. Let's write our expression for Ka. Here is our Ka, again, products over reactants here. And now let's plug in, just like we did before, our equilibrium concentrations. And here we go right here. Now, at this point, you might be seeing that I've got a little bit of a problem. I do not have a value for Ka, and I don't know what my x is either. I cannot solve this equation if I have two unknowns. So how do I fix this? I'm going to use the pH. Remember, pH is your negative log of your hydronium concentration. Your hydronium concentration is your value for x. So let's figure out what that concentration is using our pH. So plugging in our pH like so, our hydronium concentration is 1.7 times 10 to the negative third. Again, that is our value for x. Now we have a number that we can plug in for all of these x's to calculate Ka. All right, so here is our new expression with all of our x's plugged in. It's a little bit large and it looks a little bit messy, but it's really not that difficult. Just when you're putting this in your calculator, be careful that you are putting the scientific notation in correctly. And we get a Ka of 3.47 times 10 to the negative fourth. In some ways, I find these problems actually a little bit easier because you're not making an assumption and you're dropping an x and checking with the 5% rule. You just need to recognize that your pH is the key to finding your value of x, which then gives you your Ka. Next, let's deal with the percent dissociation problem. This problem reads, the percent dissociation of a 0.85 molar solution of hypoiodous acid is 0.0485%. What is the Ka of hypoiodous acid? Just like I did in all of my other problems, I want my balanced chemical equation. Here it is right here. Yep, it's in equilibrium. This is a weak acid. Let's fill in the rest of my ICE table. My initial concentration is 0.85. Again, I have no product, so that means I'm going to have minus x, x, and x, and then my equilibrium concentrations are right here. After you work a couple of these problems, you start to see the pattern here, right? Okay, so what is our expression for Ka? Here is our Ka right here. Let's plug in our equilibrium concentrations, and our Ka looks like this. Now again, at this point, you're saying, I don't know what x is, and I don't know what Ka is. I cannot solve this equation with two unknowns. This is where the percent dissociation comes in. So our percent dissociation of our acid is simply going to be our x over our initial concentration times 100%. Does this look familiar? It should look familiar because this is how we always check our 5% rule. All right, so we know our percent dissociation, the problem gives us that, and we know our initial concentration of our acid, so I'm just plugging my numbers in here. I can solve for x. And I get an x that's 4.12 times 10 to the negative fourth. So now I can just take this x and plug it into my expression for Ka and calculate Ka. All right, here it is right here. Here's x plugged into all the places it needs to be plugged in. Again, just be careful with how you put scientific notation in your calculator so you don't spit out the wrong answer. And we get a Ka of 2 times 10 to the negative seventh. These problems can feel daunting at first, but hopefully after working just a few here with me, you see that there is a pattern to these problems. Use that pattern to your advantage. I hope you found this video helpful, and thanks so much for watching.